All right, so settle down and we'll get started in a bit. Okay, so we are nearing the tail end of our sort of deep dive into ROS, and I had planned that this could have been a lab session today, but I thought it would be easier if we cover some more ground in learning about some more concepts, and then in the next time we meet, we'll have a elaborate, hands-on session, so we can cover much more topics rather than just one or two topics at the time. And so today, as you can tell from the slide, the idea is to finally get to understand what a node does, right? So for us right now, a node is this high-level construct that we have seen examples of. We are familiar with what its sort of the job is to publish to topics or subscribes to topics using some messages. But today we will actually look at examples of some of ROS Python API and how do you design your own node, or how do you let ROS know that this piece of Python code is supposed to be a node, and how do you publish and how do you subscribe. So again, much of this material is sort of adapted to make it much more straightforward and suitable for the course from the ROS wiki. And so I will touch upon, I would say 90% of the key concepts that you need. Some of them may be very straightforward, but again, these are things that I have to cover at least once so everybody's on the same page. So previously, in our lab session and in the we haven't had a lab session on that yet, but in the previous lecture, we covered what was the Catkin build system and the file system of ROS. We spent a lot of time in looking at the details of why this exists. And the key thing to take away from that was that ROS uses Catkin as the main CMake build system to compile all the code, and that you have to create this workspace, which is this structured, the example is shown on the slide, which has these folders called source, development, install, build. And when you initialize a workspace, some of the things are automatically populated for you. And so within the source folder, which is mostly of interest to us in this course, resides our packages of interest, right? And recall, a package is nothing but a collection of many, many ROS nodes and some custom messages, some services, and we saw examples of the TotalSim package. So within the source folder of the workspace, you have packages. Packages themselves have their own source or script folders where the ROS nodes reside. And so the idea today is to understand what that node can look like. And we'll start from sort of very, very basic concepts. We also spend time talking about, in order for ROS to know that a particular folder is a legitimate package, we need the presence of two files. So we need the cmakelist.txt and the package.xml. The package.xml is the package manifest file. It contains the metadata of interest, but more importantly, it contains the list of dependencies for Catkin. And these are build time dependencies and runtime dependencies, what have you. So we went through an example of this file. Then we also went through what CMake list does, and you'll actually see in just a second an example of why we would care about using CMake list. The idea was the CMake list.txt is also auto-generated as a template, but you have to edit occasionally. This is the input the build system will take, right? So this is all of what we have covered, and in the next lab session, you'll create a workspace, you'll look at these files, edit them with your metadata, so on and so forth. So at some point, I must have mentioned that ROS, to develop applications in ROS, you have some libraries which are available. So C++ is perhaps the most widely used library and the most expansive, very versatile. It's fast as well. So many of the AutoWare nodes, which are the open source ROS perception planning control stack, they are written in C++ just because it has more sort of robustness to it. ROS Python is also very popular. It's simpler, and many of the nodes on our F110 car are actually written in using the ROS Python API. There are other libraries as well, but today we will take a look at the rospy sort of API, the client library on Python that ROS supports natively, and we'll take a look at some of these examples of how do you invoke this ROS Python library to create, initialize a node, publish data, subscribe to data, and use some very other critical functionalities of ROS nodes as well. Examples, or the client library examples. So this is what I would say is a simple example of a node which is tasked to publish some data. Okay, so we'll go through all the aspects in more detail in this lecture, but just visually, that's why we like Python, because you can literally read this out and make sense of what is going on. So at the very beginning, you import the ROS Python library. This has to be done for everything else to work. Then we are importing from another library called standard messages, this class called string. Okay, and so we'll see what the string as a class contains, what kind of message type it supports. So we import some sort of a message, we import the library. Then, without going too much into the details of the publisher yet, we are creating a handle using the ROS Python API called .Publisher. So I am creating a handle called PUB and saying that this is a publisher. And we'll see what is the syntax in detail of a publisher. I'm also telling ROS that this entire executable is a ROS node. So I say rospy.init node and followed by the node name. This is very important. Without this, we don't know whether this executable has anything to do with ROS or not. We can control things about the publisher in this case by controlling the rate at which messages will be published. And finally, there are some constructs that we can invoke. So, hey, this is the equivalent of a while loop. So you say while a flag called rospy.is shutdown. So while the value of the shutdown flag is not true, let's publish messages. And then we say go to sleep, but this is not your ordinary sleep as in Arduino where you have to specify the amount of time you have to sleep. ROS is very smart as a meta OS. So when you say r.sleep, it will automatically figure out how much I have to sleep in order to maintain the publishing rate. Okay, so this is what keeps the node alive. So this loop continues, and it continues as long as someone presses exit or Control C or ROS node kill, and then this flag is set to false, and you will break out of this loop. Right. So intuitively, this is what a publisher does, and then we will see detailed examples of sort of instances of or snippets of these codes in just a minute. Okay, so we always begin not in this is the first line of your script, but we always ensure that your Python script somewhere ROS Python init node must be present, right? So we have to invoke ros.python.init followed by the node name. Also, what is sort of highlighted as something that you have to pay attention to is you can only initialize one node in one script. If a single executable contains multiple init nodes, it will throw a warning. Okay, so this has to be done only once. In fact, as I've said, if you are doing many things in a single node, it's the better idea is to break it up into different nodes, right? So that's the modularity of ROS. So while this is more than enough to initialize a node, the complete syntax is you can initiate another argument to be true or false. So this anonymous argument is a Boolean argument. You can set it to true or false. I did cover this in passing, but this is where we are telling ROS that when this node is actually launched, so I would say ROS run package name and this my node name. If your anonymous is equal to true, ROS will append some pseudo-random sequence next to the name of the node to ensure that if someone accidentally launches a clone of this node, then the previous node is not killed, because you can keep launching the node with the same name, and ROS will keep launching these nodes with different pseudo-random sequences, because in ROS, remember, names in ROS of nodes have to be unique. You cannot have two nodes which have the same name. While we are on this topic, it's worth mentioning that in the publisher-subscriber context, the subscriber actually doesn't care what is the name of the node who is publishing. Okay? The subscriber only cares about topics and message types. never ever did teleopkey care that the node which was running is called turtlesim, as long as it was subscribing to pose or command velocity and things like that. So just something to keep in mind. But while saying that, it is important that no two nodes have a same name, and if you don't want to deal with that yourself when you have a large code base, you can simply set the anonymous flag to be true. So very straightforward. So we just saw how do we invoke a node, or how do we make a node alive. Let's also, before we look at the interesting parts, look at how a node is shut down. So there is a flag called rospy.shutdown, and this is automatically going to reflect the execution state of the process. So as long as this is false, you are doing some work, because while not true, do some work. So this is, we just saw an example of that. But you may be wondering, well, how would a subscriber keep itself alive, right? So while can we again use the same thing that while the flag is not true, listen to some messages as a subscriber. But then what does it mean to have a rate at which you listen to messages, right? So your publishers has a rate. So what I'm getting to, and I don't want to confuse you unnecessarily yet, eventually yes, there is another option called rospy.spin, which will also keep your node alive. rospy.spin acts like rospy is shut down as well, right? So spinning just means consume some CPU cycles while you are waiting to do something. So you can use either or to monitor whether your node is alive or not, and that's how you check for if your node has been killed, or basically if your node has been killed or not. Okay, there's multiple ways, and you can choose one based on what the node does. We'll see examples, because that's the best way to sort of wrap your head around why would you use one versus the other. This is for the sake of completeness. We do use this sometimes, but while the previous flag was monitoring is shut down, you can also invoke another rospy client functionality called on shutdown, meaning that if the node has received a request to shut down either through Control-C or ROS Node kill, before it actually dies, you can still do some last-minute work. Think of it as that, right? So rospy on shutdown is being sent a callback function or a handle, and this handle, for example, rospy on shutdown, the name of the handle is my hook, and then in this function my hook, you are in this case just printing shutdown time. So why would you need this, right? Let's think about why this exists rather than get bogged up with all this syntax. Here's an example. Let's say you are running your F110 code, and you want to ensure if for whatever reason the laser starts reporting no data, which means the ROS, the Hakuyu node or the laser node is no longer running, then you would want to make sure that that information is either conveyed to others, or some safety condition is reached, or some stopping criteria is invoked. So if the Hakuyu node gets killed for whatever reason, you can have an on shutdown function or a handle within that node which does something for safety of the car, so it stops, because it's essentially running blind if it has no LiDAR data. Okay, and we'll revisit this later, but this is also part of the killing process of the node. Okay, so now we know how to initialize a node, how to kill the node, or at least wait for it to be killed. Let's now actually look at publishing and subscribing in terms of the Python API. So at the heart of this publisher-subscriber construct is we have to exchange messages. So before showing you how do you publish and how do you subscribe, let's just wrap our head around different ways of forming messages. And this is again intuitive, but I will cover these three different ways because all of them are valid, and different ways have different merits compared to each other on how do you actually construct messages in ROS. So here's the sort of background for this. We have seen that many packages contain a special subfolder called MSG or message, within which usually reside some data structure definitions in .message files. And once again in the lab, we will see an example of it. So here's just some random arbitrary example. You have some package. Within that, there's a subdirectory called message. And my data structure is called foo.message. I don't care what the exact structure is. So what ROS does is when you initialize your CMake CMake list.txt or the package.xml, you point it towards this directory where the custom message file resides. And during the build time, Catkin will create a message class for you. So remember how I was importing string from some standard message dot something something. That was created as a class by Catkin just based on the directory structure of the custom file, right? So let's take a look at some examples. So rospy will take the message files and generate the Python library for them. So you can do something like import the entire library and then create an empty message of the type string, as is shown here. So you're just appending the library with .string, or you can import just string because you know your publisher will only deal with strings and create an empty message directly like this. Both are sort of valid. Again, this is sort of teaching almost Python at this point, but we'll cover it for completeness.
There are some Python nodes and some C++ nodes.
So as I've said, in totality, it doesn't matter because nodes are executables and they can talk to each other over topics. But a single node cannot be both, right? So a single node is either Python or C++, but a Python node can talk to C++ and vice versa. Okay, so just to convince you further, if you actually go to any of the packages in ROS, so standard messages is nothing special. It's just a ROS package. And just like any other packages like TurtleSim, it has its own ROS wiki page. And you can see it has been supported from quite a while in ROS. It goes back all the way to very beginning of ROS itself. It supports some common message constructs. So you can actually look at all the message types that standard messages supports. It's a very long list. No point in going over it. But I want to show you in this list is present the .message file for string. Okay, so standard message is a package which has some message folder within which is present string.message. And what is this data structure for string.message? It's actually just a single field called data of the type string. So no surprises there. This is a very simplified message class. Okay, so this is where ROS finds that this is the string message class you mean because it has the path to standard messages. And that's what it means when we say from standard messages import string. Okay, just for another example, this is another message class we've been spending some time on. We have a different package called geometry_messages, which has the package type, the message type called twist.msg. And this is the data structure for twist. We have seen that linear and angular are vectors with x, y, and z. Right, because command velocity, which was being sent by teleopkey, was an example of this sort of a message. So you don't have to remember any of this, but you need to understand where this is coming from because at some point you will write your own custom messages. I guarantee that. In fact, we'll see an example of that by the end of this lecture. Okay, so we know how to create empty messages now. How do you actually initialize some content in the message based on the data structure? And here is where there's 3 different ways. They are all equivalent because at the end of the day, they are accomplishing one job, which is I have to create a message with some relevant data. And so here are 3 different ways of filling up a message with some data that you may want to send over a topic. Okay? And why are we looking at this? Because we need to understand how to build messages before publishing or subscribing them. So the first way of adding data to a message is what is called explicit way, or one with no arguments, and you'll see why it's called no arguments. And it's very straightforward. What you do is you first create an empty message object. So message is of the type string. It's empty. And then we fill in the field within that data structure with our data. Okay, so note that I knew that this empty object has a field dot data only because I am familiar with the string.msg file. Otherwise, there was no oracle which told me that the field is called data. Okay, so you can say message.data is this value, hello world or whatever, and then you have created your message sort of packet, and then you can just publish this packet. You will see an example of that in a bit. So it's called no arguments because when you created the message, you created an empty sort of message object. In this case, it was of type string. Let's look at an example where you have some arguments. So another way of constructing messages is called inline or in order arguments. And the difference here is when I create the message object or the handle to the message, while creating that, I'm already populating the field as well. So why is it better? Maybe because I don't need to know exactly what the field name is. I just know that string accepts some string message. So I just have to provide the value of the message directly when I, in the order or in line when I'm creating the instance. The important thing is string is maybe not the best example because it only had one field called data. And so we can say, string and then hello world in inverted commas. But here's another example. So let me highlight this. So look at this. We have standard message.message, and then there is a different sort of message type called color RGBA. The requirement of in order arguments while creating a message is that if this message type has, let's say, 4 fields, so one each for the RGB value and one for the alpha channel, during the in order arguments, you have to provide values for all of them. You cannot leave anyone or skip one out. It will throw a warning. So when you invoke a message using this style of messaging called in order arguments, you have to provide a value for all of them and in order. That's where I guess in order comes from. So in this example, color RGBA has 4 fields and need to provide 4 floating values in order for this to be a valid message. Okay, and just so it's complete again, we can look at standard messages / color RGBA. The dot message definition is exactly that. So it's different from the no keyword or sort of no argument style, where you don't need to remember the names of these fields, so you don't need to remember these RGBA constructs, but you still need to know that this message type has 4 fields that you have to fill. Okay, so slight detail over there, but important one. So let me cover the last one and then I'll pause for some questions. The last way is also equivalent to the first two. You can pass some keywords during the inline argument. So compared to the previous example, instead of just saying hello world, I am saying which specific field of the message has to be assigned this data. And the importance of this is, again, the string is not the best example, but look at the color RGBA. I know the color RGBA has 4 fields, but maybe I just want to update the blue channel. And everything else should be default or whatever is the previous value. So I can pass or construct the message in the style of inline argument without having multiple empty messages and then fulfilling them. But in this case, I have to specify the name of the field which I want to update. So as sort of simple as that. Okay, so I know again this is maybe somewhat trivial, but trust me, these are the things which make or break your code. So you need to either adopt one and stick with that and always use the same sort of message construction, or when you switch between them, it's actually beneficial, because some structure of messages will have maybe 14 different fields. So in that case, it won't make sense to pass 14 values all the time. Maybe some of them don't need to be updated. So there you can use keyword argument to construct the message, or even the no argument style of message passing. Goes without saying that for whatever values you don't specify as keywords, they take on some default values. Okay, in this case, the default value is 0. And side note is you can always choose what the default value can be. So to summarize, we have keywords style of arguments in which you need to specify the actual keyword of the data structure of the message and then assign the data to that. It's concise, and you can see what field is getting updated. In the in-order arguments, the benefit is that you get to see the entire message which is being passed. So that's also beneficial, right? If you are passing some command velocity, then it's good idea to use in order so that you know there's nothing default being passed that you are not aware of, because it's explicit in the way the message was constructed. Or if you don't care about concise code, or you can obviously trade for more lines of code, but then again you have to remember the field names as well. So it's a choice, okay? And we don't force any particular choice on you, so you won't get any credit deducted for using whatever as long as it works. That's what we care about. Okay, so that was about constructing messages. And the reason we want to construct messages is because we want to publish and subscribe to them. So let's just jump on to that part. So the next functionality in the Python API is how to publish and how to create a topic to publish. And again, like with everything else, it's quite straightforward, but I will cover everything. So you create a handle, and you have rospy.Publisher is the API functionality you want to use. It can take different arguments. The three most important ones that you will definitely use are the name of the channel or the topic on which you want to publish. That's expected. The message type, which governs what messages are being sent on that topic. So already, here's another insight. If a topic has been defined with a particular message type, you cannot publish another message type on that topic. Okay, that will again throw an error. So if a topic called laser scan has been defined with a message type called scan, then you cannot publish images on that topic. It just won't work. Okay, so the arguments are the name of the topic, the name of the message type, and then finally input called queue size or buffer size, right? So as a publisher, you may want to have a buffer such that if for whatever reason your messages are not meeting the rate at which you have set your desired publishing rate to, at least they're not getting lost. So there's a certain sort of a buffer size where messages are getting stacked, and whenever the master has an opportunity on the TCP socket, it's being sent. Why would it not be sent? Because there may be competing messages. We sort of saw that when we have the teleop key and the circle competing with each other to take the control of the swimming of the turtle. Okay, so straightforward format, we say that this node is a publisher with these three attributes of the publishing, and then you can simply call the handle.publish and just pass it the message. Yes? Very good, right? So like I said, these three are the basic things about a publisher. There is some fine level control. So you have control over whether it should be last in, first out, or first in, first out, sort of a dropping policy. I think by default, it resorts to just, if there is no space in the buffer, nothing would be buffered, right? Yeah, so if there is no space in the buffer, if it's full, then your new messages are not getting buffered. They're just getting dropped. So just so that I know you're awake, can someone tell me what sort of style of message passing is this? It is inline arguments because we don't care about the field, and we know that string only has one field, so we are specifying all possible fields. Okay, so good, you are awake. All right, so we've just seen this. Take home message rospy.Publisher as topic name, class, queue size. So here is some of that extra stuff that you can also invoke when you have a publisher. I will say it, but once again, these are special circumstances that I want you to know exist, but we may not use them from day one. So one sort of high-level thing I've always maintained, including the main sort of title image of this presentation, was a publisher has no idea who's subscribing and things like that, right? So it's agnostic to how many subscribers or which subscribers. Well, let me break that notion, a big notion for you. You can actually receive a callback when someone subscribes to you. You don't know which node subscribes to you, but you can receive a callback so that you can maintain some notion of whether someone is connected to you or not. Or maybe a publisher expected that 3 nodes would subscribe, and then all of a sudden there's 4 subscribers, so it's a security check. You can invoke some flag that something fishy is going on. So we will not really use this, but I want to mention it because it is there. And similarly, there's an argument called latch. It's a Boolean flag, and what this controls is that sometimes if the subscriber gets dropped, and you are publishing some values, maybe you are not publishing at a very high rate, you can latch onto your previous published message for a certain amount of time. Okay, so it will, if someone subscribes again, they will get old data because you were latched onto that. Once again, don't let it confuse you. These are just special features. And if and when you are needed to use them, we will definitely make sure we tell you about them. All right, so just like you can create different message types, I'll go over this a little bit faster. It's obvious that you can also publish in different ways based on what message type you are creating. So here, we've seen an example. We are invoking the handle .publish function on this handle pub, and within this parentheses, I'm not only creating a new instance of the string message, I'm also populating it using the sort of explicit style. And similarly, I can do the in order style as well. Maybe this is the best example. So here, when I invoke .publish, I am passing values for all the fields of this RGBA. Okay, so I'm directly passing the values because previously I would have told ROS that this topic requires RGBA type of messages, so I can directly pass values in .publish as well. Is it clear? And then finally, you can also do the keyword style, so you can directly say just update this value of the message. You don't have to create a new message type every time. ROS knows that this publisher is publishing on these standard type of messages or whatever you have defined. Okay, so the point being, just like you can create different ways of packaging a message together, you can basically apply that concept to publishing as well. Okay, these are just some rules of thumb of how do you choose a queue size. Note that if you set your queue size to 0, it actually defaults to an infinite queue size. So don't do that, because that will invoke some memory problems. So you can set it any number starting from 1. And a good rule of thumb is that if I'm publishing, say, at a rate of 10 hertz, so 10 messages per second, I should set the queue size to be equivalent to that rate. Or here's another example of why you would not want to have a large queue. Maybe you are publishing some sort of data such that the subscriber always needs the latest instance of that data. Okay, so a camera is publishing images, and my obstacle detector doesn't need all the images. I just need to know what the camera has published right now. So I am willing to accept the latest image at the cost of dropping some buffered images as a subscriber. So in that case, you can actually set your queue size to be just 1. So even if the subscriber is not receiving all the images, whatever it receives, you are ensuring is the latest because there's no queue. Does that make sense? So you would want to play with the queue size, but this is a rule of thumb that you can keep in mind. When would you break this? Well, if you are publishing on multiple things at the same time at different rates. Okay, so then you want to basically have the length of the buffer such that it accounts for all the messages that this node has to publish. So remember the buffer size applies to each channel as well, but it's the property of the node. So you can control certain topics are sending more messages and certain topics are getting updated less frequently, so you can adjust the queue size accordingly. So let's take a look at an example. I think this is the best way to actually understand, just short of having to write code, which you will very, very soon in the next lab. So I'm going to walk you through the entire publisher, and feel free to interrupt me if anything is not clear. So yes, this is a Python script. You can say that up top. Then we import the Python library, rospy. We have already seen that from this library called standard messages, we are importing a class.string, so that we can use this type of message or create objects of this class of type string. And underneath the hood, Catkin knows that based on the string.message file, it has created this class for you to import from. So it knows where standard messages is located. So we define a function. In this case, the name of the function is talker. You'll see why. What is this function? And within this function, I first say, let me create a handle and to rospy.Publisher. So I want to publish something within this function. The name of the topic I'm publishing to is called chatter. And chatter will always publish messages of type string, which is a part of standard messages. So how does ROS know what the string is? Because of this line. And I have created the queue size of equal to 10. Then I'm telling ROS that this is actually a node. Okay, so if I just leave it at rospy.Publisher and not include line number 8, ROS will not know this is a ROS node. So this is very, very simple. I say rospy.initNode, again using the rospy API. The name of the node is talker. It just happens to be the name of the function. That's not a requirement, but a good practice. And then in this case, I'm actually setting the anonymous namespace argument to be true, which means when I invoke talker, the real name of the node will be talker underscore some pseudo-random sequence that ROS will append, because anonymous is true. So let's keep going. Since this is a publisher, I need to tell ROS how often to publish. So I can invoke another rospy functionality called rospy.rate and give it an argument. And this is the hertz. We have seen you can validate from the command line ROS topic hertz, name of the topic, and it should reflect the same number. And then this is where the publication actually occurs. First, we create this loop to say, keep looping as long as you don't receive any shutdown flag. So while rospy is shut down is not true, so while not is the actual sort of function over there. I first create a string. Yeah, this is incorrect. I'm not creating a message. I'm creating just a string over here. So my string is hello world, and then append this text with, we haven't covered this, but we are appending this with the sort of ROS OS time. So just to keep track of when this hello world message was sent. You could even just add a for loop or an index to keep incrementing every message. But let's say we are just creating a string right now. And you need not worry about line 12, but what rospy.loginfo does is it will echo the message first of all to the screen, right? So if you don't have this command, rospy.loginfo, what will happen is when you run the talker node, so when you say ROS run package name talker.py, the terminal will remain empty even though messages are being sent. So what rospy.loginfo is saying is also echo the messages to get printed in the session of the terminal. But the real stuff happens on line 13. We have created this string, and we are just passing the value of the string directly to pub.publish. Okay, so this is publishing the string on the topic called chatter. How does ROS know that this hello string is valid? Because we know that this should be a message of type string. And so, hello string is indeed a message of type string. Everything falls into place. So straightforward, you are doing stuff in order. And then we've spoken about this briefly. Since this is a while loop, you have to wait to maintain this rate of 10 hertz or whatever the user requires. Here's a caveat. You can't just put any rate and expect rate sleep to always work. Why? Because all this stuff is also taking some execution time, these lines above. So if you're doing some heavy lifting in your while loop, it might be the case that you are not able to maintain your desired hertz rate because there's just simply not enough time to send packages with that number of time and do the compute for every package. Okay? So regardless, when that is not the case, rate.sleep just will sleep long enough to maintain this rate of 10 hertz. So this is all our function called talker. How does this actually play out when we run this node? We have our Python main thread right here that you are familiar with. So here we are saying just call this publishing function as long as there is no exception. So what will happen is when someone kills this node or an exception occurs or I press Control C, this rospy.isShutdown becomes false. So we break out of this loop, and you can break out of this execution using this interrupt exception. So there are different ways of exiting the node. This is just one example. So the main part I want you to take away is how to publish, what is rospy.isShutdown and rate.sleep, and the general sort of workflow of a publisher. So any questions on what is the intention of this publisher and how it is using the different Python API functionalities? Yes? Good, right? So the question is what will happen if we wanted to use rospy.spin? And you'll see an example a little bit later. But the idea of spin is it is also sort of monitoring whether the node is alive in the background or not. So you don't need to use the while loop and spin at the same time. So if your node is just publishing, this will work. Why do we prefer this way of working? Because by using rate.sleep, we can ensure that a rate of publication is maintained. rospy.spin is more useful when you are also subscribing. And I will show you an example where a node is both a subscriber and a publisher, and we will use rospy.spin over there. Okay? All right, so let me cover that part because I also want to show you how these nodes run in just a few minutes. And so we are already there. So we've covered publishing. So subscribing is very, very similar. Okay, so here's the very intuitive way of telling ROS that this node is a subscriber. Much like publisher, you say rospy.subscriber, name of the topic, name of the message structure on that topic, and instead of the queue size, because a subscriber doesn't make sense to have a queue, it will have a callback function. So anytime a subscriber receives a message on this topic, this callback function is invoked to parse the message and do some interesting stuff. Right? So let's look at an example. Everything is pretty much the same. We are still importing the same stuff, but we have our function called listener, and within that, we first initialize the node. The subscriber is also a ROS node. No new news over there. Then we say this subscriber is subscribing to the topic called chatter, which the talker was publishing to. And so whenever we get a message on this topic called chatter, we invoke a function called callback, which is defined right here. And the callback will simply read the data. In this case, it's just echoing the data on the terminal. And to go back to the previous question, what is keeping this node alive? Line number 11. rospy.spin, because the subscriber is event driven. It's waiting and listening on messages, but between messages, there's no rate of listening. So it's just spinning cycles between messages. And there is no is shutdown flag for this functionality. So hopefully that clarifies that question of why would you use is shutdown versus spin. So I believe we'll walk through this code as well. It's very, very short compared to the publisher actually, but everything up top is same as before, at least in our example. It will not always be same for all nodes. I hope that's obvious. And then we tell ROS what is the name of this node. Previously, our publisher was called talker. This node is aptly named listener. And also, we have set anonymous equal to true. So this is listening to what? It's listening to messages of type string being published by some node on the topic chatter. So for every message on chatter that is received, the callback is invoked, which is up top. And rospy spin simply prevents the node from exiting, as keeping this node alive by consuming cycles between these events. And what is the callback doing? The callback is get the ID of this node or caller ID. And you will see an example of this to understand what this returns. Plus, it will just print out the contents of the data it received. Now, here's a happy coincidence. I didn't plan this, but this is a good opportunity to get a little bit deeper. When I receive a callback in my subscriber, this function is invoked, and I'm naming the contents of that function data. But since I know that the message is of type string, I know that a subfield of this structure of message I have received is also called data. That's why you have this weird data.data stuff over here. Okay, I could have avoided it by calling this something else, but it turned out it's actually good because we can now understand. So the subscriber knows the message type. That's why it can decipher the exact field it wants to echo. Okay, so yeah.
So what if you get the message type wrong in string, like on your subscriber? What if you put the wrong kind of message type?
It will return that it didn't find during runtime. Yeah.
So can a single publishing node publish, I guess, different?
Yes.
A
publisher can publish as many nodes and subscribe to publish to as many topics and subscribe to as many topics. Okay. But remember the core. If you are doing too much in a single node, split it up into multiple nodes. Okay, that's never lose thought of that very simple principle. So let's look at F110. I know it's a little bit, the text is small, but I want to at least give you an example of how we use this on the real car. So shown here is a node called dot. Okay, for some reason I think I've lost functionality of my remote. It's fine. So shown here we have an example called Ackerman twist.python. Just very quickly, the purpose of this node is it receives data in a particular message format and converts it into some geometrical format and publishes that data out again. We will not get too much into what format this is. That's something which we will cover in this course actually in a couple of weeks when you get your cars. So we will import, rospy. We are importing twist messages from geometry.twist. So here's an example. This node is publishing on 2 topics. So we have 2 handles. One handle is publishing on a topic called servo. So servo is used for the steering on our F110 cars. And the other handle is publishing to the topic motor speed. So this is the drive, right? So steering plus drive equals motion in the car. So you can see we have told what are the sort of message types, and the queue size is 1 because we always want to send the latest value of the steering and the velocity command. This is your Python main thread. So notice earlier on I had a different function in which I was describing the subscriber and things like that. It's not always necessary. In fact, this one also breaks that sort of coding format, but this is also valid. Within the main thread, doesn't matter if it's not visible. What we are trying to cover is we initialize the node. So we initialize the name of the node. We are subscribing to some channel called command velocity, which is of the geometry message / twist. So it's the exact same twist message that TurtleSim uses, which is why I said if you can get TurtleSim to swim autonomously, it will work on the car as well, because most of the messages are the same. Right, so we are initializing our message, we are subscribing, and then we are spinning, because this is a subscriber part. Every time we get a message on the subscriber, we invoke this callback function starting from line 18, within which essentially, this callback function is invoked, and we are doing some conversions to a different sort of output. And once we have converted that, here is where you are invoking the .publish handle command from the ROS Python API to publish the actual messages on the topics which you have defined up top. So all of this is using these Lego blocks of the ROS Python API to achieve an example on the car where you are subscribing and also publishing within the same node. Okay, so that's why it's important to at least get used to some of this basic functionality of how to write a subscriber and how to publish. Okay, so about ready to wrap up. We previously saw that you can create a package by using a command called catkin create package. In fact, this is an overview of some of the things we will do in the next lab session. What we will do is we'll create a package called beginner tutorials, which just depends upon other packages. So standard messages, rospy and roscpp. In fact, for our lab, we don't need roscpp. We can just say standard messages and rospy. Then we say within the source, we have created this package. What this will do is create a subdirectory called beginner tutorials. It will create the package.xml and the cmakelist.txt for this package as well. And then when we go to the root folder and we will build this new package to essentially build this, this default code out. And during our lab session, we will create these two nodes that I just spoke about today. So we'll create a node called talker.python, which will be a publisher. This node does exactly what we covered in the lectures. It's going to publish to a topic called chatter with the same queue size, anonymous equals true. So notice how this is, since this is only a publisher, it's using the is shutdown flag rather than the spinning stuff. And then we'll also create a subscriber called listener.py in our lab session, which the code will look something like this. We don't have to go over it again. And then we will run both of them and see how one is publishing and the other is subscribing. We'll play with some rates and some namespace flags and things like that. Okay, so I have a few minutes, so let me show you an example of how this actually works. It will only take a couple of minutes. Interesting, I think my machine is running slow today. Okay, almost there. So let me launch a bunch of nodes. So first thing we'll do is launch ROS core. Our ROS core runs without any trouble. Now I'm going to say, well, let me first show you where the beginner tutorial is located. In fact, we'll use a command we've studied previously. I'll use ROS change directory and directly type the name of the package called beginner tutorials. And in fact, I already know that within this package, there's a subdirectory called scripts. So just to save time, I've directly changed my workspace sort of path to that, okay, in one command. And to convince you, there's a bunch of scripts in the beginner tutorials. The one I'm interested in right now is talker.python. Very quickly, let's just take a look. So it's doing just one job. We are initializing the Docker node. Notice that the anonymous is false here. We are publishing on chatter messages of type string. What are we actually publishing? We are publishing hello world followed by the time. So let's see it running, and then things will become clear. So I don't need to be in this directory anymore. So now I can say ROS run beginner tutorials docker.python. Just like TurtleSim, I have created my own new node. And when I run it, you can see it's sending messages hello world followed by this number, which is ROS's interpretation of time. We'll have a dedicated part of a lecture on how ROS handles time. It's a very important thing, but you can see the Docker is just publishing as it has been commissioned to. You can validate all of the other things that we did previously. So let's start with ROS load list. Okay, this checks out. We have Docker is the only node right now. Then I can say, well, what about ROS topic list? What we expect is chatter should be one of the topics. Sure enough, it's here. I can keep going with exactly what we did with TurtleSim. I can say, well, ROS topic type chatter. I want to know what type of messages can be published on chatter. It's a standard messages string, and I can then say, can you show me what is the format of standard messages string? And it says it is a data structure with a single field called data. Everything is exactly what we covered. Or I could have saved all this trouble and simply said ROS topic info and chatter. And it will tell me that yes, this is the message type. Docker is publishing. Notice that the name is Docker and not some random sequence because anonymous was set to false, and it has no subscribers right now. So let's fix that. Also in that directory, we will write a node called listener, which is subscribing to chatter. And so listener is now echoing messages that it is receiving from chatter. In fact, there's one point I want to make here. If I show you, so let me go back to the code for a second. So within our subscriber, if we look at what it is supposed to print out on the terminal session using this log info, there is something called rospy.getCallerID. So if I open a new terminal session and say ROS node list, look at the name of this node. It's listener underscore some random value. But this random value is fixed because once the node is initialized. And if we go back to our terminal, every message also has this listener underscore random value before the hello world stuff. So this is where the get node ID is coming from. Okay, so what is going on? Maybe as long as we have this session open, I can even say RQT graph, and sure enough, we have a Docker publishing on chatter, subscribed by a listener. And we can keep playing however we want. I can say ROS topic hertz. I want to confirm indeed the messages are being sent at 10 hertz. So if I say ROS topic hertz, well, sure enough, the rate is almost 10. Okay, it hit 10 right about here. Okay, so in the next lab session, this was very, very fast. We will actually create a Catkin workspace, create a package called beginner tutorials, create these two nodes, Docker and listener, and understand the notions of publishing and subscribing. Okay, so do remember to bring your virtual machine /ROS for the lab session on Thursday. And with that, this is all I wanted to cover. If there are no questions, we can end the class here.